Have you ever tried to pinpoint to things perfectly at the exact same moment, only to find that observing one inevitably blurs your knowledge of the other? In the fascinating realm of quantum mechanics, this isn't just a metaphor. It is a fundamental law. Conjugate variable pairs refer to specific pairs of physical properties in quantum systems, such as a particle's position and its momentum, or its energy and the precise time it possesses that energy. The meaning of these pairs is that you cannot simultaneously know both properties with absolute, perfect precision. When you gain more accurate information about one, you inherently lose accuracy about the other. This intriguing limitation stems directly from the wave-particle duality inherent in quantum mechanics. Every quantum entity, whether it is an electron or a photon, behaves both as a particle and a wave. A particle that has a very precise position is like a very short localized wave packet. But such a wave packet is actually made up of many different wavelengths, and a precise wavelength is what defines momentum. Therefore, a precise position means an uncertain momentum. Conversely, if you have a perfectly defined wavelength, representing a very precise momentum, that wave would stretch infinitely through space, making its position completely uncertain. This profound interrelationship is mathematically captured by the Heisenberg Uncertainty Principle, which states that the product of the uncertainties in a conjugate pair must always be greater than or equal to a fundamental constant called reduced Planck's constant divided by 2. So, practically, what does this mean for scientists and engineers working with quantum systems? It means that when you design an experiment or make a measurement, you are making a choice. You can choose to measure a particle's position with very high accuracy, but you must accept that your knowledge of its momentum will become correspondingly fuzzy. Or, you can measure its momentum very precisely, knowing that its exact location will then be less certain. This is not a flaw in our measuring devices. It is a fundamental property of nature itself, telling us something profound about the very fabric of reality at the quantum scale. A deeper mathematical insight into conjugate variables involves what are known as commutation relations. These pairs are often referred to as non-commuting observables because the order in which you measure them matters, mathematically speaking. This non-commutativity is the bedrock of the uncertainty principle. Another fascinating consequence of this concept is zero-point energy. Even at absolute zero temperature, particles cannot be perfectly still or perfectly localized. The inherent uncertainty in their position and momentum means they must retain a minimum amount of vibrational energy, an intrinsic quantum jiggle, that cannot be removed. Understanding conjugate variable pairs is absolutely essential for grasping the truly unique and often counterintuitive nature of the quantum world. It helps us interpret experimental results, design more effective quantum technologies, and ultimately reminds us that reality at its most fundamental level is far more nuanced and probabilistic than our everyday experiences suggest. This core concept is the foundation upon which much of quantum physics and its applications are built, guiding our exploration into new frontiers like quantum computing and quantum sensing.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.